So today let us start our discussion of connection formula. So we already discussed why we need connection formula, and what we have seen is when we have a potential which is slowly varying and it is having bound state something like this, okay, and the energy of the particle is something uh, this way. On the classical turning point, your WKB approximation is going to be not valid. You have seen it already. But this is valid in the inside this region, this classically allowed region. This is a classically allowed region, and this is a classically forbidden region, but classically forbidden region. This is a turning point. Okay, so at the turning point or nearby to the turning point, anywhere close to the turning point, this is not going to be valid. So this is valid inside and outside. So we need some sort of connection at the boundary which connect between the wave function. As you know, it is a continuous thing. So how do we do that? The idea of doing this is like we will develop a scheme to understand the Schrodinger equation at this particular point, and then we solve the Schrodinger equation and we will be having a solution form, and you compare on two limits. If you're seeing, for example, at this boundary, you can uh, check the connection formula deep inside this. Deep inside this, it has to match with your classically allowed region, that wave function that you obtained. You have a functional form of that, so it has to match with that. Outside the region, again, you know the wave function at this region. That also obtained from the WKB approximation scheme. So then you can connect with that particular form and compare those equations will give you whatever necessary value that you have. Okay, so now we will not be discussing each of these boundaries separately. We just need general formation of that. So I am just putting this area, this boundary, I am just going to expand. And you know, this is a slowly varying potential, and slowly varying potential means this variation is going to be really small. So if I zoom in to this particular area sufficiently, I will get a straight line at that area, right? Zoom in sufficiently so that you will get a straight line. So it can be any of the boundary. And one side I will be having classically allowed region, and another side I will be having classically forbidden region. That is the only difference. Otherwise, both are same. So if I'm taking this boundary, I will be having classically allowed region here and classically forbidden region here. Here, that will change. That is only difference. And if you want to do it, maybe the slope will be changing. So this is more applicable for this case that I'm drawing. So we need not to discuss it separately. Okay, so this is going to be my turning point, and I call that as x naught. Okay, so this is x naught, and at x naught it corresponds to the energy value is going to be E. This is your potential energy V of x. Okay, so I'm taking this is my classically allowed region, and this is forbidden region, and this is the turning point. Now we have to develop a Schrodinger equation formation here. Before that, let us write the kind of potential at this zoomed up version. So I just want to write the potential here. That potential is going to be okay on the or anywhere close to the turning point. I can approximate this as a straight line. I will write the expression for v of x as, how do I write it? It's a straight line, and I know, okay, let me take this as a axis here, and I will be having my initial value. I need y-intercept and a tangent to specify that equation. Sorry, not tangent, slope. So here I can take this particular value. At x0 I know what is going to be the value here. As it is a turning point, the energy is going to be, potential energy is going to be the energy of the system. So that is going to be E0. Your y-intercept is going to be E0. If you are writing a line formula, and you need to have the slope of this particular line, and that is nothing but dv at that particular point by dx of x0. So what is the slope at that point? That is going to be this quantity, and mx, and x is going to be nothing but x minus x0. Okay, so this is the way I write my potential, and you can write the slope with some other constant c or something. So v of x is going to be some energy. No need of writing e, no, sorry, e c into x minus x naught. So that is how your potential is going to be. Now what we have to do is, at that point or at this kind of a potential, we have to solve our Schrodinger wave equation. So the time independent Schrodinger equation we have modified slightly into this form, like d square psi of x, we have done it for one dimensional case, dx square plus p square of x psi of x is going to be equal to 0. This is the equation that 1 by h cross square factor is there. This is the expression that we have. And what is this p of x? P of x is nothing but root 2m e minus v of x. Okay, so I modified, or at the region that I am interested, I have an expression for my potential. I can modify this by just substituting that value. That is going to be root of 2m e minus v of x is again having an e, and another thing is minus cx minus x0. So the first term will be cancelling, e will be cancelling with that, and we will be having a minus sign and a c constant x minus x0. So that is going to be our p of x, the momentum at that position x. Okay, so we got p of x, and we can just substitute that value on the differential equation. This is going to be like d square psi of x divided by dx square plus p of x is going to be this, and square of that, that is okay, this plus will become minus now, 2mc by h cross square already there, x minus x naught into psi of x equal to 0. So this is the expression that we have to solve, and I have to modify this expression slightly into the form of a non-equation. So for doing that, I'm going to put some substitution here. So that substitution is like 2mc divided by h cross square whole power of 1 by 3 into x minus x naught. This quantity and 1/3 of this quantity I am going to put not 1/3, power 1/3. I'm going to call this as y. Okay, now I have to find d square y, uh, and I have to substitute that value here, and whatever here, you know that this is like to the power 1/3 we have taken, so you can substitute this entire term as 2mc by h cross square, uh, yeah, 2/3 into 1/3, so that 1/3 and this x minus x naught will go as y, and you will be having and 2/3 of that remaining over there. Okay, so when you're putting d by dx square, just take differentiation of that 2 times, obtain that value, and you will be having something like 2mc by h cross square coming in. You'll substitute it on terms of that, and what you will be having here is 2/3 of that, and d square psi of x divided by, now the variable is changed into y, d square y, and minus this term 2/3 of this quantity is there already here, an additional factor, so I will take it commonly outside, and the remaining expression is going to be, here I have a y and a psi of y, sorry, this is also y, right? Now the wave function is in form of y, and that is a new expression, and this quantity will disappear from the expression now. So the expression that we have to find out of the solution, Schrodinger equation now become d square psi of y divided by dy square minus y psi of y is equal to 0. Okay, so this is a simple looking expression, and the solution is known as, solution to this kind of an expression is known as Airy functions. Airy functions. Okay, so the form of the expression is as follows. So there are two such kind of functions. First one is ai of y, another one is bi of y. Two of them are there, and the complete solution is going to be a linear combination of that. So ai of y is going to be of this form: 1 by pi integral 0 to infinity cos z cube divided by 3 plus zy dz. This is going to be ai of y, and bi of y is going to be 1 by pi integral 0 to infinity again, and there are two functions here: an exponential function which is having the power minus z y minus z cube by 3. In addition to that, we have one more term, that is sine z cube by 3 plus zy dz. So this is going to be the expression for aiy and biy. That's a general functional form. So what we need to know is how do that behave at like if you're taking the origin as x naught, then how do that behave far away from that point x naught. This is something that we want to know, or we need to know how to that asymptotic behavior of this function at 2 points. So those equations can be expressed like this. So, or the value of this value of this particular function, ai of y, I can write this at two particular region like this. So this is going to be equal to minus pi y whole to pi square y to the power minus 1 by 4 sine of 2 by 3 into minus y z, sorry, 3 by 2 plus pi by 4. Okay, and this is when your y is very less than 0. When y is less than 0, it's a very high negative value, then this is going to be the solution of that. And if you have a positive value, this is going to be something like half pi square y whole raised to minus 1 by 4 exponential of 2 by 3 y raised to 3 by 2 y greater than 0. Same way, you'll be having another solution, which is b I of y. Again, two form. One is when y is very much positive and y is very much negative. So this expression is going to be minus pi square y whole raised to minus 1 by 4 cos 2 by 3 into minus y to the power 3 by 2 plus pi by 4, and y less than 0, and another one is pi square y raised to minus 1 by 4 exponential 2 by 3 y raised to 3 by 2. This is when y greater than 0. Okay, so what is our y actually? How do we define our y? Y is like okay, it can be any region on x minus x naught. X minus x naught is positive. That means y is going to be positive. So when is x minus x naught is going to be positive? On the case that we have taken, x naught is here, x minus x naught. When x is this side, it is going to be positive. So that corresponds to the forbidden region, classically forbidden region. Or the second case corresponds to or the classically allowed region, when negative y indicates classically allowed region. So to just emphasize that this is y less than 0 corresponds to classically allowed region, and here you have classically forbidden region. Classically forbidden region, same classically allowed region and classically forbidden region.